second module here in Unit 3. So this is Module 9. We're finishing up Unit 3. We've been talking about the idea of correlation, and all the time we've been referencing kind of this background line that I've sometimes been drawing. And so our goal is to actually calculate that line now. And so fitting a line, linear regression. So the regression term there is the line itself. This is that one algebra technique we need from previous algebra classes you've taken. So this the only small thing to refresh on from algebra. In the Canvas notes we have some stuff there. Okay, so I'm just going to kind of quickly highlight this. You can read through this more if you want. There is a way to identify kind of forensic remains, and one of those is to look at like how long bones are. And so someone did that to kind of measure Amelia Earhart, a famous pilot in the 30s and 40s. And so in general, I'm not going to worry about answering that question, but you can just see the idea here. So there is the length of your forearm. These are for 21 female college students. So forearm, I don't know, probably, I think that's this piece here, from your elbow to your wrist, roughly somewhere. And so inches, from a little bit less than 8 to a little bit over 12 inches, then comparing to their height. And you can see there's a pretty strong pattern, but right, in course, it's not a perfect pattern. Some people just proportion-wise have longer and shorter arms relative to their height. And so our idea of linear regression is specifically what is the line that goes closest to all the points. On Canvas, you're going to see a little bit more detailed description of that. What really happens is we measure the distance. Well, we actually, mathematically in the background, it's a little more complicated, but the final outcome is the line where when you measure the distance and then square it, so you can actually imagine making little squares there. Why do we square it? Just to make that distance positive. So we really actually just subtract, and it's not technically a distance, and then we square it. But it's the line where when you draw all of these distances and then square them to make it positive, they're all supposed to be squares of whatever size makes sense for that square. When you add up all those squares, the line that has the smallest total squares area is the answer for the line that's closest to all the points. And that's your officially called your least squares regression line. I won't call it that. I'll just call it the regression line, or the regression equation. Probably the two things I might say. Mathematically, these are the slope intercept idea of the equation of a line, right? So we often write it a little bit backwards. Like this is mathematically the same thing, but it's just which one do you put first. But mx plus b, b plus mx would mean the same thing. It's not a dramatically different form, right? So when you have an equation of a line that looks like this, m is your slope, and b is your y-intercept. So slope, right, is a relationship of how steep the line is. It's always measured as the idea of if you move over 1, how high in the y-axis are you going up or down. You've seen the fraction version a lot in algebra classes, so like the rise over run. But when we use decimals, it's always the idea of moving over 1. So small change there. And then the number that's not multiplying the variable is going to be the y-intercept. That just comes from inputting 0 for the x variable, and you get out the y-intercept. And so that's where the line hits the y-axis. For example, though, that's not right now 58, because that's not at 0 on the x-axis. Algebra, we might kind of always imagine graphing the 0 area of the xy graph, but for data, we usually zoom into where the data is. It's a very, very small thing to be careful about. And so in stats, the other big thing we do is we usually label the equations. You'll see that StatCrunch does this on its own with the actual name of the variable. So forearm length and height. So if you want to calculate someone's height, and it's estimate, the word we will specifically use is predict. But if you want to predict someone's height, it's 39 plus 2.7 times their forearm length, both of these variables in inches. And you can estimate their height. The better the correlation, the more accurate the height. Okay, so here are some examples. These are 34 adults who were physically active, trying to predict their weight. So the predicting is the response variable. Trying to predict it from their bicep versus thigh girth. So if you measure the size of your bicep versus thighs, which one better predicts your weight? Well, that's going to be the context of the question here. So these are the same 34 people, so the weights are the same, two different measurements, and so the context of the question is which one is better. So Adriana has a thigh girth of 57 centimeters, which would put her visually somewhere right around here. We're going to calculate it to figure it out, so we're not going to do that visually. 55, so I might be a little off there. Somewhere right around there. And a bicep of 25, that'll be easy, that's right on the graph. Bicep of 25, there. So you can see, it's going to be somewhere around 70, and then somewhere around 55. These are both in kilograms. Roughly multiply by 2 to estimate her weight in pounds, in case kilograms don't make, in case you're not familiar with kilograms. And so which of these is more likely to be the correct answer for her weight? So Adriana's can have 3 measurements right now. Pretend we don't know her weight though. If we have her bicep size versus her thigh girth, which one better predicts the weight? So you want to use the vocabulary of our section. How do we describe the pattern, quantitative data, the shape, sorry, not the shape center spread, the form, the strength, and the direction. But form, we just ask ourselves, is it linear? These are roughly linear. The thigh one doesn't quite have a clear linear pattern, but I think it's close enough. The bicep clearly has a linear, very good linear pattern. There's nothing really wrong with that. Okay, so then what is the other things we can use to describe these patterns? We talked about form, so the direction, they're both positive, that makes sense. If someone has larger biceps or larger thighs, you either way predict they have larger weight. Right, in real life we don't know if that person is very muscular or not, but we're still gonna normally think they're gonna weigh more. And then lastly is the strength. And so which one is going to be better is the main context of this question. So first though, we will predict both. So thigh and then bicep. So her weight is going to be 7.85 plus 1.07 times. So thigh one is first, and that's 57. Make sure to use an advanced calculator that does this all for you. You don't want to get order of operations wrong on this question. So have something you can type it all in at once, press enter. I'm getting 68.8. Specifically 0.84. All of the data is rounded to 2 decimals, so I'm going to keep at least 2 decimals. And then her weight, as you can see, was, I think I estimated my graph wrong. The graph is right, but it's just you can't really get as accurate. The bicep one, we were thinking it was going to be closer to 55. So negative 13.45 plus 2.67 times 25 centimeter for her biceps. $53.3. Alright, those were roughly right. I don't think I have anything calculated wrong. Okay, so which of these two numbers is more accurate is part B. So one thing we can't do is we can't just make something up and find some number that relates to these. That would not be something accurate. That is not necessarily allowed in our class. Just be careful that you don't make something up based on the methods, you want to pick which variable is more accurate here. And so how can you do that? Here you can do that by answering which variable had a stronger correlation and then use that. Let me give you an example. You might take in a traditional version of this class, you have a Unit 2 checkpoint, a Unit 3 checkpoint, and then you might have like Exam 1 that relates to those, and then Exam 2 that relates to other ones, and a final exam. And I might say, what's the best way for me to predict your final exam grade based on all those different inputs? Which one is more likely? If you had a first exam and a second exam, or is it your homework percentage, or is it your Canvas checkpoint quiz percentage? And I would study that and pick one that I use to predict everyone's finals. Okay, so which prediction do you think is more accurate? We can do that by which has the stronger correlation, and that would be the bicep one. The bicep points look a lot closer to the line and have a stronger pattern. So the bicep one, the weight using the bicep, so the weight is going to be 53.3. So the other one we essentially ignore and say the bicep calculation is more accurate here. Why? It had a stronger correlation. All right, and so this is our last topic already here. We have these numbers in our linear regression equations. What do they mean? Well, we already know that they mean the slope and the y-intercept, but what do those tell us in more word problem context? And then this is our last topic that finishes up all of Unit 3. Okay, so mathematically in algebra type class, the y-intercept is when your x value is 0. This is the kind of general algebra answer. And the slope, rise over run, change in y divided by change in x is what we answer there. And it also can be interpreted as the change in y for one more x. And so it turns out that's the one we're going to use. But let's give a specific example. So you have predicted rating of a 77 breakfast cereals, and we have the predicted rating of that cereal. So someone went and already found ratings for 77 cereals and their sugar content, and it turns out that there is a strong general relationship between these patterns. You can see graphically here that the more sugar, the lower it was rated. Right, the equation for that, 60 minus 2.43 times sugar. So it's minus there because the slope is negative. So first thing, what is the y-intercept and what is the slope? So first we do have to be able to identify it. So the slope is the number that multiplies the variable, and you do need to bring either the positive or negative with it. So slope 2.43. Y-intercept is the number by itself, 60. This time the graph, the y-intercept looks like 60. And then this one's actually a little weird. The y-intercept is here at 0. The graph actually shows a little bit part of negatives. Software does weird things sometimes. It just picks random stuff. Okay, so what do these tell us in context of the problem? Context means like the vocabulary words of the problem. So if you're talking about cereal, sugar, and ratings, you should be using those type of words. So the y-intercept value is 60. Y-intercepts always mean that the x input was 0. And so that tells us if a cereal has 0 grams of sugar, the predicted rating is 60. That's all. That style phrasing is always true. It's 0 of whatever the x variable is. You should say the x variable in words. Then the predicted y variable, whatever that is whatever the number of the y-intercept is. So these are pretty short. Keep a little note card of that style phrase there. All right, now let's try the slope. So the best way to use the slope, especially for decimals, is the change when it's one more in the x-axis. That is most commonly that's always going to be our preferred way. And that's actually very common in different kind of math and science, and that's the word of per. Like if someone says um, miles per gallon, that's a fraction. The denominator is gallons, but it really specifically means per 1 gallon, right? 30 miles per gallon, 30 mpg means 30 miles for 1 gallon. So it's actually very, very common to reference for 1. All right, and it also just means kind of dividing the fractions. All those different ways is what it means. All right, so our slope here is negative 2.3. And so what this tells us is, think about it as a fraction. So then your rise would be negative 2.43 over your run of 1. We're always forcing it to be 1. And so in context words, so this phrasing here, our predictions for Consumer Reports decrease 2.43 points for each additional gram of sugar in a serving of cereal. So that is a phrasing that explains that in words that most people can understand. All right, and I think we have a few examples on the next page, and we'll try one of them. All right, so we have bicep girth and weight. Same one as before. So your weight, negative 13.45 plus 2.67 times your bicep girth to predict your weight, right? It's not saying for sure that's your weight, but a good prediction. It looks pretty well correlated, so it'd probably be a pretty good prediction. Okay, so our first is to interpret the y-intercept. So first we need to find the y-intercept. So that is the number not multiplying the x variable, and so negative 13.45. Its units right now are the same as the y-axis, so kilograms. So this interpretation is a little shorter, a little more simple. So it comes from 0. It's kind of an actual coordinate on the graph. It comes from having a bicep girth of 0. So for a bicep girth of 0 centimeters, we would predict a weight of negative 13.45 kilograms. Hopefully you say, that whole thing doesn't make any sense. The y-intercept frequently is not all that useful, but this is what tells you if it's useful or not. You need to imagine constructing this sentence to help you determine if that's really useful. So there's two terrible things with this. One, the weight is negative. You can't have a negative weight, and you also can't have a bicep size of 0. Bicep size is 0. If your size is 0, you have no biceps, you have no arms. And presumably someone with no arms is not included in this data set. As you can see, the smallest bicep size is only a little smaller than 25. So this one is not useful, but this is kind of the sentence in context that really helps us determine that. Right, and so what is the slope here? The slope is the number multiplying the variable, the x variable. So the slope is 2.67, but identifying that really doesn't tell us much. We want to think about what that means. And so that's the phrasing back here. And so you are going to use kind of for each additional somehow. However you grammatically phrase that, it's not a big deal, but for each one more x, whatever the x is, whatever the number of the slope is the change in the y, whatever that variable is. So you're just going to fill in all the numbers. So for each additional centimeter of bicep girth, we predict weight. It's positive, so to increase by 2.67 kilograms. So every time you move 1 on the x-axis, you go up by 2.67 on the y-axis because it's positive. All right, there's another one you could try there. If you have questions on that, you can come to Stats Fun Time and ask some questions. You can also post that in, there's like a general discussion post, maybe you can post that there. Or you can just email me if you have a quick question on it, Pronto or our Canvas inbox. There are a few additional topics in Module 9 that are on Canvas. Those will show up on your unit checkpoint for Unit 3 on Canvas, but those won't show up on the Mastery quiz. So if it wasn't here in these notes, I don't expect you to be able to answer that Mastery quiz question on it, but you are expected to answer that on Canvas. So there's a few additional topics. I highlighted them, I introduced them a little bit here. One of them is called extrapolation. That's what happens when you look at data outside of the range we're studying. And then some of them are more advanced on ideas called the standard error. And there's an idea there. That one is not on the Mastery quiz. And also, if you just take the R number and square it, we very boringly call that R squared, it actually represents something different, something additional that's really interesting, and that is also not on the Mastery quiz. So those two topics, those are at the end of Module 9, I believe. Those are kind of additional. They're topics we're supposed to cover, but I just don't think we need to cover them that in depth. So they're on Canvas, and then they're on the quizzes on Canvas, but they're not on the kind of official Mastery quizzes. Right, so that ends Unit 3. Unit 4 is going to be another question about relationships, but with different types of data. So I'll see you in Unit 4, Module 10.